Okay, two problems of Leonardo of Pisa are very important and are discussed in your book. One is given a non-square number, such as number 41. Uh, Number 41 um, is the non-square number. Please note that when this book is talking about number, it means not whole number, rational numbers. So 41 is just one example of a whole number in this case. It can be written as sum of two squares. Well, two squares we can try. 41 is 1 plus 40 doesn't work. 4 plus 9 plus, it seems like 16 plus 25 works. So 41 is a non-square that is sum of two squares. It says find another pair of squares. So besides 16 and 25, what is the other square having this number as their sum? So we are looking for another pair of numbers, b squared, and another one, b squared, so that their sum is 41. So this is the problem that Leonardo solves. And the second problem is how many pairs of rabbits can be bred from one pair in 1 year, given that each pair begins to breed in the second month after its birth. So it doesn't breed after, right after the month. So it has to wait 2 months to breed, producing one new pair per month. So this is also, this one is from Libre Abaci. And the first one is from the Libro Quadratorum, or the book of the squares. So to solve the first one, we need to know this interesting theorem or the fact that applies equally to whole numbers and rational numbers. So if you have two numbers that are both sum of two squares, so for instance p is aa plus bb, b times b, uh, so this is taken from a paper by Euler, and they are not writing as an exponents. So and q is another number, sum of two squares. So these are just two numbers. Could be p could be a square or could be non-square. Then we can write, in fact, p as sum of two squares. As you can see, if we write the squares that their sum results in p and q in a matrix, so we have a b for p, and we have cd for um, q, then these squares are squares of the column multiplications, which is AC plus BD, and the other one is the square of the determinant. So for instance, if we have, say, as a toy example, 5 is 1 squared plus 2 squared, and let's say 2 squared plus 3 squared is 9 plus 4 or 13, then we can write 13 times 15, 13 times 5, sorry, or 65 as sum of two squares. What is squares? Okay, you can pause and think about that, and then see what I write here. So, well, uh, uh, the answer would be, writing this matrix would be, we have 1, 2, and 2, 3. So column multiplication, then add them together. 2 plus 6, 2 plus 6 is 8. And then we have 1 times 3, 2 times 2 is negative 1. In fact, I can write 1. So it's 64 plus 1, and this is 65. It works. All right, now going back to the problem of the squares. This is just illustration of that by an example. So we know that 41 is a sum of two squares, right? 5 squared and 16 or 4 squared. Now we can take any two square numbers whose sum is square. Okay, so any two square numbers, 25 and 144, their sum is 169, which is a square number. We could have taken 3 squared and 4 squared, which their sum is 25, right? Or 9 or 16. So we can find plenty of these. These are Pythagorean triples, right? And now look, we form the product of these two numbers, right? One is the 41, which is our target number, and 169 is sum of these square, that's the square itself, right? Now, once we do that, we find two squares whose sum equals this number, all right? Equals what number? This number. And we learned how to find that. Actually, these are two pairs. This is another pair. In fact, using that notation that we had, we can write 5, 4, and for 169 we have, this is 5 squared and 12 squared, which is 144. So we can see that the product is in fact 25. All right, 25. 4 times 12 is what? 4 times 12 is 48, which is 73, plus the determinant, if you recall. So it's 60 minus 20, or 40 squared. This pair is coming from that theorem. This one may be another method that we didn't discuss in the previous example. So going back to the problem, therefore, we can find these pairs. All right. Now, choosing one of these, we can write 73 squared plus 40 squared is 41 times 169. So dividing the sides by 13 squared, which is 169, these two cancels. Then this quotient rule for the exponent results in this equation, which tells us 41 is written as sum of two squares. Of course, we're talking about the square numbers, and in this book, numbers mean rational numbers. What rational numbers? Well, 73 divided by 13 squared. This is the first square, and the second one is 40 divided by 13 squared. And for this pair, we can write another one. So we have 80 squared plus 23 squared equals 41 times 169. Once again, dividing these two numbers by 13 squared. These two cancel, and then we can see that another pair, 80 divided by 13 squared plus 23 over 13 squared is also 41. So besides the pair 25 and 16, which their sum is 41. We found another pair, and in addition to that, even another pair. So 3 different pairs that their sum is 41. So this is a pretty remarkable result and solution that is done by Leonardo of Pisa, or Fibonacci. Now we are going to look at the next problem about the rabbits.